Ciao, and welcome to the Frontier Space Podcast, a dialogue about how space technology and exploration are transforming our solar system. We're honored to meet you and have you on the Frontier Space Podcast, Dr. Kevin France.
Thank you. Great to be here.
How are things in over there in Boulder, Colorado?
Life is pretty good here in Colorado. It's fall is the best time of year along the mountains here, and so it's nice when it gets a little bit cooler and you get to spend full days outside.
How is the research progressing and everything with your missions?
So we took data from the Sistine Mission when it launched on July 6th, and the data looks really good. We're in the process of analyzing it now, and the payload is in transit, a very slow transit back to Colorado from the Northern Territory now. And so we won't really get a look at the instrument again probably until close to the holidays, because it takes several months to get back to the East Coast of the United States, and then it has to be shipped over to us. So, but we've got the data and are working on it now, and we'll be planning to present it at a conference here in a couple of months, and hopefully the paper will be ready in 2023.
I was reading more about you in particular and some of the incredible things you've done, and you've been the PI for over 20 NASA funded science and instrument programs and over like 50 or something publications. So could you share more about your projects and your career and
Sure. So yeah, I've been really fortunate to be involved in basically space, research, astrophysics from observations made above Earth's atmosphere for the majority of my career now. And it's kind of a dumb luck story. I was an undergraduate at Boston University, interested in research. And so I went to the department office and asked, what kind of jobs do you have for people who want to learn more about research? And one of the jobs they had, which sounded cool, was to work on a small satellite project called Terriers. And so even though I didn't really have any of the qualifications in terms of coding or background or any of that, they hired me. And through that project, I was able to get involved with sounding rocket research and was able to go to White Sands Missile Range in February of 1999, the launch of a rocket called Spinner. And it was just the greatest thing. And so when I was applying to graduate school later, I applied to programs that did instrumentation work from space. And, I've kind of been on that path ever since then, as a student, and then as a postdoctoral researcher. And now somehow I found myself in charge of some of these things, but it's very interesting because the type of science that we do, we really have to be in space to do it, and building things that work in space is just inherently challenging, but also very exciting. So it's been a good ride so far.
what have been like maybe the top few I think most meaningful missions and research for your career?
I think probably the first sounding rocket mission that I worked on as the principal investigator was very exciting. Somebody I probably worked in rockets for about 13 or 14 years before I took over my own program. And so to get to the place where you're not just working on one of these missions, but you're working on your mission was really very cool. And I guess some of the other highlights, we've being involved with the Hubble Space Telescope. I was on an instrument team that built an instrument that's on Hubble, and have been an observer with Hubble for a long time now. And in my opinion, I think the Hubble Space Telescope is probably the most important scientific instrument that humankind has ever created. And so to be able to be a part of that and actually do the science that Hubble is doing is, I think, is very exciting. And then maybe my other top three would be when we launched and then started collecting science data from our CUTE satellite, which is a CubeSat mission, which is NASA's only second small satellite mission for astronomy. And so it was really very much an experiment to see whether or not we could, you could give a university and a bunch of students a relatively small amount of money and to build a high quality scientific instrument. And so CUTE's up there right now observing short period extrasolar planets that are transiting, passing in front of their parent star and collecting spectroscopic data on what their atmospheres are like. So I'd say those are probably my top three.
Awesome. We were wondering, what is the Sistine Telescope, and the purpose and kind of its how its features will enable the data and discoveries.
Right. Sistine, I won't even attempt to give you the acronym. Is one of my worst acronyms of all time. But it is a sounding rocket-based telescope that has two purposes. One is to study the radiation from nearby stars to understand how they influence planets, extrasolar planets. And then Sistine is also a prototype instrument for future ultraviolet telescopes and spectrographs that we hope to incorporate into large NASA missions going forward. So let me talk a little bit about the CUTE science. I'm sorry, CUTE science, the Sistine science, and then I'll mention a little bit about how we use Sistine as a technology platform for doing cool new things that we have to have to build ambitious new instruments. So one of the things that we know about, we know this here on Earth, that and we know about, or we strongly believe about extrasolar planets, is that the influences of their parent star are rather profound. So most of Earth's climate is driven by what happens on the sun, and so we expect that to hold true for other planets around other stars. But most stars are not like the sun, so we need to understand what we call the spectra of those stars, essentially how light is distributed throughout the electromagnetic spectrum. How variable are they? Do we have events like the coronal mass ejections that we see on our sun? Do we have things like energetic flares and X-ray and ultraviolet light? Because all of these things drive the photochemistry and essentially the physics of the atmospheres of planets that orbit these stars. So it's I could spend a long time talking about this, but basically every part of the star spectrum is important for a different factor on the exoplanet's atmosphere. So Sistine studies what we call the far ultraviolet part of the spectrum from about 100 to 160 nanometers. And this is particularly important for driving photochemical reactions in planetary atmospheres. So the destruction of water and methane and carbon dioxide to create oxygen in the atmosphere, and also to liberate atoms to escape to space. A lot of that is driven by far ultraviolet photons. So what Sistine is designed to do is to go out and make measurements that we don't have the capability to make with, say, the Hubble Space Telescope, of nearby stars and measure their far ultraviolet properties. And then we use those to make predictions about what types of planetary atmospheres we expect to see around stars like those, with instruments like the James Webb Space Telescope, or future instruments of like a large optical telescope that would be searching for the signs of life, and say like the 2030s and 2040s. So we're really laying the groundwork now to understand what types of stars we should be studying to survey for the signs of life on planets around these stars. So that's kind of the science background to Sistine, and but it's also, like I said, it's a technology demonstration platform. So essentially, every optical component in Sistine is a research and development project. So Sistine was the first telescope to apply these new aluminum-based coatings. Aluminum is incredibly reflective. It's a great thing to put on a telescope, but it's also very sensitive to oxygen in Earth's atmosphere. So if you lay down a layer of aluminum on a telescope mirror and you don't put anything on to protect it, it will oxidize very quickly and essentially lose its shininess. So the Sistine mirrors have a new kind of experimental coating procedure put on to protect the aluminum, and this is we call this enhanced lithium fluoride, and so we put this layer of lithium fluoride down on the mirrors, and it had only ever been demonstrated on little laboratory size samples before we built Sistine, which has 4 optics that are all coated in aluminum with lithium fluoride, the largest being 1/2 meter, so it's about yay big in diameter. So we're trying to scale up from what we've demonstrated on the really small scale in the lab to something that is representative of the types of astronomical optics that we would want to build for larger missions in the future. So Sistine is basically a technology test bed for that. We're also flying the largest ultraviolet sensitive cameras that have ever been developed, and so that's all part of the motivation, is that we've got this science goal, but then we build this unique instrument where we're able to try out all of these different technologies and build them into essentially a prototype package, where we not just see how they work as individual things, as individual components, but how do they work as part of a real system, because that's how they're ultimately going to be used on a future mission. And so we really want to see how how all these pieces go together. And so that's really where the idea for Sistine came from, and kind of what we've been doing with the timeline of the mission since, I guess, we started building Sistine in about 2017. And yeah, so that's kind of the science and technology story for Sistine.
It's very cool, and and interesting. We're wondering, with the spectral resolution of, I think it's R 10,000, what does that mean in terms of what you can image?
Right. So there's a couple of different ways to describe how finely you can break up the star's spectrum. And so one convenient way is this resolving power, and really it's by its mathematical definition, it's the wavelength you observe at in the numerator divided by how finely you can sample that spectrum in the denominator. So if you had a very finely resolved spectrum, like a very high spectral resolution, that resolving power number would be very high. So that's one metric of being able to describe the spectral resolving power, or the spectral resolution of an instrument, in terms that basically make all instruments comparable. So yeah, so that's how it's a pretty common way to describe a spectrograph.
Thanks for clarifying. And so with the sub-arc imaging and it looked like 5 minutes duration on orbit, wondering like how much atmospheric data could you collect and analyze?
Yeah, geez, I don't have the exact number of photons that we collected, but you can create. So in our flight of Sistine 3 from Australia, we resolved Alpha Centauri A and B and collected essentially a pretty high signal to noise, a relatively high fidelity ultraviolet spectrum of both stars in the course of the about 5-minute observing time. So if I were to guess, I'm not sure exactly how many actual photons we collected, but the number is probably of order 100,000 photons from each star, something like that.
It seems like this is more than enough to interpret the atmosphere for and effects of the UV rays.
Yeah, it should be. It should be as long as you can make a relatively high fidelity spectrum. You should be in good shape.
So these are the photons at the upper edge of the atmosphere of these nearby planets we might visit one day.
Well, these are the photons from the parent stars that we observe at Earth. But once we've measured that, we can. It's pretty straightforward to do the transfer to how many photons the planet's atmosphere observed. This is as long as we know the distances to us and the star, and the distance between the star and its orbiting planets. We can do that conversion, and then we can run a calculation of what types of, say, photochemistry we would expect on that orbiting planet.
So with a sounded like this was like suborbital, but really like kind of like a low cost mission too, with such a short time.
That's right. Yeah, it's definitely cheaper to fly something that just probes the near space environment as opposed to putting something in orbit. Although maybe that's changing a little bit as we get cheaper and cheaper access to launch vehicles. But it's also a matter of mass. Sistine, the whole payload at launch is something like 1,200 pounds, and you can launch a CubeSat. I mean, something that's this big by this big for a couple $100,000 now. But I don't think you can launch an 1,100-pound payload into orbit for that cheap right now. So yeah, it's definitely a low-cost access to space, but it's not orbital.
And what were some of the engineering systems and kind of like the innovations and challenges you overcame with Sistine?
Oh, lots. So originally the telescope that we had fabricated was not basically not made correctly, and so we had to do a lot of scrambling as we were building up for the first launch of Sistine to get essentially kind of a reworked primary telescope. That was definitely something. These advanced optical coatings that we were applying to the mirrors, it's a research and development project. So some of the optics came out really spectacular, like a great demo of what we had expected, and some of them missed the specification by a little bit. And so we had to kind of go back to the drawing board and ask ourselves, rerun all the calculations that we had run previously, and said, can we still do this science with the optics as they are? And so there was some anxiety there. We also had some issues with the optomechanical design of the payload. It's not very common to launch such a big mirror on a sounding rocket, again, a half of a meter in diameter. The sounding rocket environment is extremely harsh. So, the payload experiences 13, 14 Gs on launch. And so to build a telescope that is supposed to be maintained in this perfect alignment of order an arcsecond while you're shaking it in 3 dimensions with 13 Gs is really hard. And so the first time that we flew Sistine, we actually had some optomechanical problems where the telescope shifted in a way that it was not supposed to, that threw us out of alignment with the rocket's attitude control system. And so we had a lot of problems with data acquisition on the very first flight in 2019. So, every time, this is one of the nice things about the suborbital payload and the suborbital science program is that we've always planned to fly these payloads more than once. Typically, we fly a payload 3 or 4 times. And because they are research and development projects, and because we get them back, we make them better after every flight. So we incorporate the lessons learned from the last flight, and we go in and modify the payload in the downtime between flights. So for instance, we ruggedized our optomechanical design so we wouldn't see these large shifts that we saw on the first flight of Sistine, and then we were able to take it through a test program and demonstrate on the second flight that in fact we basically be able to fix the problem. So, but lots of things. This is it's very much experimental science, and it's also projects that are in part run by students, and so we have a lot of latitude towards trying things that don't work the first time, and then figuring out how to make them better.
Nice. Sounds like important demos for future telescopes and satellites.
Absolutely. I mean, that's part of why this NASA funds the rocket program is, you can do a lot of demonstration and technology advancement for a couple of $1 million before you build an instrument, that's going to go on a $1 billion class mission. It's much cheaper to work out the bugs this way before, really investing in, the full instrument development path for a large mission like, say, the James Webb Space Telescope or something.
We're really interested in also the quantifying the magnetic fields around exoplanets, and particularly the habitable identified exoplanets, and how they correlate to the UV spectrum and the distance from their host star and the and their the Alfvén waves, I think.
Yeah. So we're beginning to get hints of the magnetic field strengths on giant planets, so Jupiter-sized planets around other stars. There are a few tentative detections of magnetic fields on those planets, mainly from radio observations, so long wavelength observations from the ground. Measuring those same magnetic fields on Earth-like planets, the potentially habitable planets, is very challenging, and it is beyond the technical capability that we have today to make those measurements for a habitable planet. It's definitely an open question how important a magnetic field is for protecting, or for making an extrasolar planet habitable. We know anecdotally here in our own solar system that the planet that had the strongest global magnetic field in the inner solar system was the one that maintained habitable conditions. But again, that's it's hard to decouple that from the properties of the parent star, and so it's an area of active research about what combination of parent star properties versus planetary magnetic field are really the best for the forming and sustaining maybe a life-bearing environment. I think it's an open question.
Yeah, I think there's a lot of discovery too, and we were reading a good amount about Jupiter's magnetic field and the auroras, and also about the magnetic fields of Alpha Centauri, and how the stellar magnetic field can be used to help model the exoplanet magnetic fields. And So there's this really good paper here from 2020. This guy Klein, and uh, their research found that so Alpha had a 200 Gauss magnetic field, and this is 3 times smaller than the typical stellar magnetic field, I think. And but they did this spectral polarimetry and magnetic analysis to really image the stellar field, and they found that Proxima B is outside of this region called the Alfvén surface and zone, and so that's where no direct magnetic stellar planet interactions occur, and so their analysis suggested that that Proxima B doesn't have the magnetic field to deflect the UV rays and radiation, yes. And so it was really cool to see how they did that, and curious how this might support what you guys are doing. Yes.
Yeah, that work to use spectral polarimetry to create three-dimensional maps of stellar magnetic fields is very neat. Those the data are challenging to acquire, but they're extremely useful. Yeah, that's still the stellar magnetic field though, and doesn't really put any direct constraint on what the exoplanet's magnetic field might be. We can say things where we can make some guesses about what the planetary field strengths might be based on how far away they are from their parent star and if they're what we call tidally locked. So basically the planets may be very slowly rotating. But this is, this comes back to that same question of how important are magnetic fields for deflecting particles. And so the magnetic fields don't stop the photons from the star from arriving. And so if the star is still very X-ray or extreme ultraviolet active, it can still have a big impact on the planet. But the right field strengths can deflect charged particles that you might get with, say, the stellar wind or coronal mass ejections. So yeah, it's the stellar data is very helpful for understanding what those input conditions are and what types of planetary responses we might expect to see.
I think that should it's important missions and data to really understand the magnetic field of uh, the exoplanets. And I think the studies suggest that Proxima B doesn't have the magnetic field necessary to deflect this ionizing radiation.
Yeah, it may be. It is very close to its parent star, and this star is reasonably old. So yeah, but again, it's not a direct measurement of the planetary magnetic field. It's it's a calculation-based result.
Yeah, with these Alfvén waves, they're essentially like how the magnetic field lines around a planet or star, how they shake. So it's a function of that vibrations, and so the solar wind shakes as it shakes Earth's magnetic field, and so we can measure these oscillations and model them as a function of habitability. And magnetic field intensity. And so we're curious, like, if some of the UV spectroscopy data from Sistine or other instruments, how they could help with the data analysis and really understanding this these interactions.
Yeah, the Sistine data doesn't really tell us anything directly about the planetary magnetic field. We know that the magnetic fields are responsible for a lot of the ultraviolet radiation that we see from the parent star, um, but is not directly a measure of the magnetic field strength there. So I don't think the Sistine results are in and of themselves really telling us anything more about planetary magnetic fields.
But if we have like a CME or like a solar flare coming in at a planet, and we can see, and if we're able to model or predict or measure at the right time, how this would interact with the exoplanet, there should be observable changes in the UV spectrum,
Um,
or
yeah, there have been suggestions that that you can see the presence of coronal mass ejections through the profiles of flares in the far ultraviolet spectrum of these stars. But the Sistine data, typically for solar type flares, those timescales tend to be hours, and the Sistine flight is just a few minutes. So we don't really have enough temporal baseline to observe those same types of things. And I should probably add that there's never been a clear detection of coronal mass ejection using far ultraviolet spectra anyways. So Sistine is not really well set up for it, and it's also not completely clear that this technique would work for that.
yes. We're really interested in helping conduct some of that research. Thanks. Yes. We're also wondering, with the more along the lines of the gases you guys are imaging too, in the atmosphere, and how the UV spectrum correlates and associates with those particles.
I'm not quite sure. So you're asking how the stellar UV radiation correlates with the planetary properties?
With the observed spectra of the gas particles.
Oh, well, we don't really have any observations of Earth-like planets and the gas particles around in those atmospheres. That's what we're hoping to get some first looks at with JWST. But if we really want to study atmospheres of Earth-like, Earth twins, you might say, around solar-type stars, we're going to need an even bigger mission in the future. And that mission we're colloquially calling LUVEX right now, and it was recommended by the NASA, National Academy of Sciences decadal survey that was released last November. So we, the astronomical community, are hopeful that that NASA will invest in the recommendations of the decadal survey as they have in the past, and actually develop this large mission to find and characterize true Earth-Sun analogs. But that's a ways off.
It's exciting.
Definitely.
With the it looks like for the UV radiation, and these photons to be imaged with the ozone production and the ozone layers. We're interested in, like, if you could quantify or image how much of these gaseous particles are spaced at like up to a few thousand kilometers beyond the exoplanet surface. Yes, and if like a telescope could image those distances, or extract them from the stellar analysis.
Yeah, that kind of work is what I was describing with this LUVEX-like mission that we're hoping that NASA builds in the next 10 or 20 years. So it can be done. It requires careful separation of the light from the star and the light from the planet. But we believe it's technically possible, and we just need to, there is some technology maturation that needs to happen to develop this, what we call high contrast imaging. And when we invest in that and build the mission, there's nothing fundamental that is stopping us from doing that right now.
Nice. It was been doing a lot of research on atomic oxygen too, and so there's like 1,000 potentially a few thousand kilometers thick layer of atomic oxygen on Earth, and I'm curious how these atomic dissociation of gases might be imaged too.
Right, that's a good question. So we do have, a relatively thick layer of atomic oxygen around Earth. We typically see that in our observations as what we call a geocorona. So basically, a halo around the Earth of this oxygen. There are a couple of ways to observe that, both at optical wavelengths and in ultraviolet wavelengths. It is something that people have thought about using these future large telescopes to look for those thick oxygen layers. But I don't know that I've ever seen, a careful analysis of the feasibility of that. But, it's definitely a feature of Earth. And so we would expect it to be a feature of Earth twin type planets. But I don't have a good sense of what the feasibility of that is right now.
Just have to look more into this, and also how the UV radiation it's how it influences the thickness of the after these great oxidation events. Yes. Is we think the thickness of the atomic oxygen layer is a function of exoplanet habitability.
I don't have a sense of what I don't know what the thickness, the atomic oxygen thickness, how that relates to when and where in the sort of habitability history we certainly get lots more free oxygen after the great oxidation event, but I don't know how that translates into the thickness of the atomic oxygen layer.
I don't know either, so we'll have to do some more research. But also comparing the flux of the UV radiation with molecular dissociation, breaking of the oxygen, and how a mathematical function could correlate that with the magnetic field potentially.
Yeah, those are probably different questions, because that photodissociation is photon processes, and those photons aren't really influenced by magnetic field. Magnetic field only influences charged particles, and so I think that there are computer models that address both pieces individually, but I'm not familiar if anybody has tried to study those all in the same model.
I think so. I just have one last question here. Appreciate your time, and we're wondering kind of what exoplanets you guys plan to image, and what's next for your these epic missions.
Yeah, well, we're really looking forward to seeing what type of spectra we see from rocky planets with the James Webb Space Telescope. I think those will be really, those results as they come out, particularly for the smaller, rockier planets, will be very exciting. I believe they're starting to take that data right now. So hopefully in the next few months, we'll begin to get some answers about what types of atmospheres those planets have. And then looking farther to the future with this LUVEX mission, you know, just very interested to get pictures and spectra of any Earth-like planet around, you know, stars like our sun within the nearest, 20 or 30 or 40 light years. And it, again, like I said, it's, I don't believe there's any fundamental reason why we can't build this instrument to go do this. So we need NASA to invest in it, and so we need Congress to invest in it, and then we need, you know, we need to build it and launch it as, and we can do all these things we're talking about.
Very exciting. We'll look forward to reading more about your research and catching up with all the readings. So, yes.
Great. Well, I appreciate the invitation, and yeah, thanks again for your interest.
Time, likewise.
All right. Thanks a lot. Have a good one.
You too. See you.